Deep dive into scikit-learn's Gaussian process rational quadratic kernel. The rational quadratic kernel in scikit-learn's Gaussian process framework is a powerful tool for capturing complex relationships between data points. It provides a flexible and adaptable model for handling various data complexities, making it a versatile choice for various machine learning tasks. Understanding the core concepts. Gaussian processes GPs are non-parametric Bayesian models that provide a probabilistic framework for modeling functions. They assume that the function values at different points are drawn from a multivariate Gaussian distribution, with the covariance between points determined by a kernel function. Kernels play a pivotal role in GPs by defining the relationship between data points and shaping the smoothness and complexity of the learned function. The choice of kernel directly influences the characteristics of the resulting GP model. Rational quadratic kernel. This particular kernel belongs to the class of stationary kernels. It models a function with varying local length scales, allowing for adaptivity in capturing data patterns. Diving into the rational quadratic kernel. The rational quadratic kernel, often denoted as rational quadratic or RQ, is characterized by its ability to model complex relationships with varying smoothness. Here's a detailed breakdown of its parameters and their impact on the resulting model. 1. Length scale. This parameter dictates the typical length scale of the function's variations. A smaller length scale indicates rapid fluctuations in the function, while a larger length scale suggests smoother transitions. It's a positive value often referred to as alpha in the mathematical definition. 2. Alpha. This parameter, also referred to as alpha, controls the relative contribution of different length scales in the kernel. It represents the power of the kernel. Large alpha. This leads to a model that favors longer length scales, resulting in a smoother function with less sensitivity to local variations in the data. Small alpha. This emphasizes shorter length scales, leading to a more wiggly function that captures local variations more readily. Essentially, it becomes more similar to a squared exponential kernel. Alpha 1. This makes the rational quadratic kernel identical to the squared exponential kernel. 3. Length scale bounds. This parameter specifies the range within which the optimization algorithm can search for the optimal length scale. It's represented as a tuple lower bound, upper bound, ensuring the length scale stays within a reasonable range. 4. Alpha bounds. Similar to length scale bounds, this parameter restricts the range for optimizing the alpha parameter. It also takes a tuple format lower bound, upper bound. Mathematical representation. The rational quadratic kernel's mathematical formula is as follows. Kx1, x2, 1, 1 2 alpha x1 x22 length scale 2 alpha, where x1 and x2 are two input points. x1, x2 represents the Euclidean distance between the points. Length scale and alpha are the kernel's parameters. As described earlier, key benefits of the rational quadratic kernel. 1. Flexibility. The rational quadratic kernel can capture a wide range of function behaviors, from very smooth to highly oscillatory, thanks to its ability to blend different length scales. 2. Smoothness control. The alpha parameter provides control over the smoothness of the learned function. 3. Adaptivity. The kernel's ability to incorporate multiple length scales allows it to adapt to varying local complexities within the data. Common applications. The rational quadratic kernel proves useful in various applications, including regression predicting continuous values based on input features, classification classifying data points into different categories, time series analysis modeling time-dependent data, including forecasting and anomaly detection. Spatial data analysis, analyzing data that exhibits spatial correlations. YAML configuration. The rational quadratic kernel can be configured in a YAML file for ease of management and reproducibility. A typical YAML structure might look like this. YAML. Kernel. Type rational quadratic. Length scale 0.5. Alpha 1.5. Length scale bounds 1e-5. 10. Alpha bounds 1e-5. 10. Explanation of YAML keys. Kernel. Type specifies the type of kernel to be used. In this case, rational quadratic. Kernel. Length scale sets the initial value for the length scale parameter. Kernel. Alpha sets the initial value for the alpha parameter. Kernel. Length scale bounds defines the range within which the optimization algorithm can search for the optimal length scale. Kernel. Alpha bounds defines the range for optimizing the alpha parameter. Important considerations. Hyperparameter tuning. The performance of a GP model with a rational quadratic kernel highly depends on the values of its hyperparameters length scale and alpha. Effective hyperparameter tuning is crucial for achieving optimal results. Techniques like grid search, random search, or Bayesian optimization can be employed for this purpose. Data characteristics. The choice of kernel should be informed by the characteristics of the data. If the data exhibits strong local variations, a smaller length scale and potentially a lower alpha might be beneficial. For smoother data, larger length scales and a higher alpha might be more appropriate. Conclusion. The rational quadratic kernel offers a flexible and adaptable tool for capturing complex relationships in data. It allows for modeling functions with varying local smoothness and provides control over the model's complexity. By carefully considering data characteristics and tuning hyperparameters, the rational quadratic kernel can be leveraged to build powerful and effective Gaussian process models for diverse machine learning tasks.